Alright, so today we're turning our attention from energy and looking at momentum and impulse, two things very connected. Um, so, linear momentum, which is almost exclusively what we'll look at here, you can have angular momentum too, but for our purposes, we'll use linear. This is a quantity of motion for an object traveling in a straight line. And the letter we tend to use here is P for momentum, and it's just the product of mass and velocity, right? So that means it can have a direction, which is kind of nice. Units, obviously, just put them together, kilogram, meter per second, um, and just leave it like that, right? We don't have another special unit or something like that. Although we'll look at another way you could write it, but yeah, it's a really neat. It's a little bit different. I know we already have kinetic energy, but this is different because it gives you something that is direct, right? It's nothing squared, right? With kinetic energy, you've got v squared, so that can be a little bit different. Whereas here, it really is just like if you wanted a basic quantity of motion, it gives you that. And we'll see how this actually has a lot of more practical uses when you're solving problems than, let's say, something like kinetic energy. So, all right, so a simple example, compare the momentum and kinetic energy of a 2 kilogram mass traveling at 1 meter per second. 2 and 3, you could do this along with me. So if we look at a 1 kilogram mass here, and we want to look at the momentum, we can say P, weird for me to use red, so let's just say P equals, well, the mass is 2 and this is 1, so that just equals 2. Let's go down the line with momentum. If this 2 kilogram mass is going 2 meters a second, then P equals 2 times 2, which is 4. And if it's going 3 meters a second, it's 2 times 3, which is 6. So you can really see it going up linearly, right? It doesn't, if it gets more massive, the exact same thing would happen. It would be a nice linear relationship. Versus if we look at kinetic energy, EK would be 1/2 m times v squared. So 2.5 just sort of cancel out and give you 1. So it's really just v squared is all we're looking at here, which is 1. So EK here would be the 1/2 times 2. And now 2 squared. So we go to 4. And here it would be EK is 1/2 times 2 times 3 squared, which is 9. So you can see, like, in terms of understanding energy, that's a neat thing to understand, that as you increase your speed, your kinetic energy goes up, not linearly, but as like a quadratic. Whereas with this, it does go up linear, and that will help with certain analyses we want to do. So again, yeah, usually momentum is a direction. Often, though, particularly with linear momentum, because we're really only looking in one direction, it's just positive or negative will typically suffice. If we go to a 2D analysis, which we will, though, you would just look at, just like when we did dynamics problems, you can look at the x direction sort of independently and just let one direction be positive. Then you could look at the same thing with the y direction. So it's technically, yes, it's a vector.
Got it.
Impulse is the product of force and time that acts on an object, usually over a short period of time, to produce a change in momentum. So these two things are very linked in that way. So if you look at the equation for force, right, which is ma, but you could write that instead of a as delta v over delta t. Multiply both sides of this equation by delta t, which is what's happening here. And then on the other side, you've got m delta v. That's all this is here. And then multiply through by the m, and you can see that's really just final momentum minus initial momentum. Right, so this thing here, which we're saying is impulse, is just the change in momentum. Also you can see the units here are just another units you could use if you wanted to represent either of these things. You could say Newton seconds. I think I normally would go with kilogram meters per second, but technically, or if you're using impulse, it might just be easier to use Newton seconds, but opposite sides of the coin. All right, a little caveat here, just before I do an example. So as I wrote here, often force is not constant. So take a second and just think, what if, well, I got a little bouncy castle down here or something like that. Or better yet, like just use something like, you've got one mass here, I call that M1, and you've got another mass here, M2. And maybe these are nice, like tennis balls or something like that. It's going to be a nice elastic collision or whatever, right? Maybe M2 is stationary, M1 is moving with some V, right? So what's the force, even if you, now technically Newton's third law says, right, whatever the force of M1 on M2 is, will be the same force of M2 on M1, right? That's forces act in pairs. But suppose we just want to restrict our analysis to M2, right? And we could let these masses be, again, the same, right? Just tennis balls or something. So if you wanted to draw, if I said, okay, here is a graph, and I want you to draw force versus time, right, on M2. So this is the force of M1, which I guess I maybe could have called like A, on B, right? What would that look like over time? And again, we're looking at a very, very small increment of time, right? M1 sort of bangs into M2, and probably then M2 takes off with some velocity. So what does that look like? Yeah, absolutely. It would be curved, basically an upside down parabola, which is essentially like a bell curve. Yeah, it would look kind of like that, which, yeah, you could say is kind of a bell curve or parabola. Yeah, because, and again, just think about it, like when it, at first it's not, they're not touching, then, right, M2 at some point is just right here, right? It's just touching it, but it's not exerting any force yet, right? It just happens to be right beside it. Then it starts exerting a force, right? And that force increases and increases and increases until we get to some maximum force here. But as M1 is applying this force to M2, right, M2 is starting to move, right? It's starting to actually accelerate because it's got this force on it, and it's accelerating away from M1. And so then what's happening on this part of the curve, right, is M2 is actually moving away from M1. So there's not as much contact, and it's, it's getting away. And then eventually at the end here, it's away. They're not touching anymore. All right, so that's what you would end up with there. That's sort of what you expect. And that's what I drew here, right? So if you're looking at something like this, this first curve, like A, which I took from a textbook, that's basically what it would look like, right? But that's a little more difficult to do from a calculation perspective or when you're solving problems. And usually, just like with a lot of dynamics problems we can just use the average. And so you can see that that's a reasonable approximation where we just assume a constant force over a very small time. Again, delta t, like I said, if you look at a collision like that with the tennis balls, it's usually a very, very short time. So it's not unreasonable to just take an average force. And that would then give us, in this case, our impulse, right? The product of force and time would give us that area under the curve. Okay, so we can look at an example here. We have a 20 kilogram child runs into the side of a bouncy castle traveling 2.5 meters per second. They bounce off the wall over 0.1 seconds, then fall backwards at 2.5 meters per second. So basically just the opposite V. What is the average force on the child during this time? Right? So again, you just kind of want to understand what's happening here. I would define some direction as positive. Let's suppose we have our child. Here's our happy child right there. They got a bouncy castle. They're real happy, right? And they're running. They're running into the wall of the bouncy castle, and they're going with some, right, we'll call this, here's V1, or equals 2.5 meters per second. And like I said, I'll make that kind of the positive direction here. We can call it X, but it doesn't really matter because I don't even need a Y in this case. So just say that's positive. So it starts out positive, and then we know V2 is going to be negative. For this, though, we really just need that one equation, which was, there, right? That the impulse is equal to the change in momentum. Thus, we can say F delta T is equal to P2 minus P1. And if we look at the information we're given here, right, we have everything except for the force, right? So that means F, and we're told this happens over 0.1 seconds, equals P2. Now we're given the mass of the child is 20 kilograms. So that would be 20 is the mass, and their initial speed is 2.5 minus their final momentum, which case their mass is still 20, but now they're actually traveling at minus 2.5 meters per second. That means, yeah, sorry, silly mistake. It's P2 first, and the final momentum is, or the final velocity is going to be what I've said is the negative direction. So that will be negative 2.5 minus their mass and their initial velocity, which is positive 2.5. That'll give me 0.1 F equals 20 times 2.5 is 50. So that'll be minus 50 minus another 50, which means F will just equal minus 100 divided by 0.1, which means that the force on the bouncy castle applies to the person is negative 1,000 newtons. And yeah, that should make sense given the coordinate system I set up, right? Because I said this person is initially running in the positive direction, so V1 is positive. And so that means with this coordinate system, the force applied by the bouncy castle would be in what I'm saying is the negative direction, right? It would apply it against the initial direction of motion, and that would lead to this nice elastic collision.